I'm so glad you could make it tonight. You found Science Blanket, your quiet space for wonder. Have you ever looked at a smooth stone in your hand and felt like you were looking at a slow-motion dream? Tonight, we're wrapping ourselves in the science of the foundation, specifically the ancient, enduring life of rocks. We often think of them as cold, solid objects, but they are actually ghosts of time, trillions of mineral crystals suspended in a delicate balance between the fire of the core and the quiet of the surface. From the light, porous pumice that looks like pulled silk to the heavy, dark basalts that bring the weight of the deep, rocks are the visible signature of the Earth's invisible movement. As we begin, imagine yourself resting in a cavern of soft, glowing quartz, feeling as steady and grounded as the mountain itself. You don't need to understand the physics of tectonic pressure or the names of the mineral cycles tonight. Just let the slow, heavy permanence of the stone tuck you in. If this blanket of ancient earth helps you find rest, I'd love for you to subscribe and join our community of sleepy explorers. Now, take a slow, deep breath. Feel your lungs expand and then empty, as steady as the ages. Let the weight of your day settle into the cooling stone. Relax your jaw, let your shoulders drop, and sink into the softness of your bed. Let's explore the quiet wonders of rocks together. Let's begin our journey through the remarkable world of rocks, those silent witnesses to billions of years of Earth's history. Imagine for a moment the ground beneath your feet, the mountains in the distance, the pebbles along a riverbank. All of these are part of an ancient story, written in stone, waiting to be understood. Rocks are far more than simple, lifeless objects. They are time capsules, holding secrets about volcanic eruptions, ancient seas, and forces deep within our planet that continue to shape the world we know today. When we look at the vast diversity of rocks around us, it might seem overwhelming at first, but geologists have organized this complexity into three main categories that help us understand how rocks come to exist. These three types are igneous, sedimentary, and metamorphic rocks. Each type tells a different story about the processes that created it, and each has its own unique characteristics that make it special. Think of these categories as three different chapters in Earth's autobiography, each revealing something profound about our planet's past and present. Igneous rocks are born from fire, from the incredible heat that exists deep within the Earth. These rocks form when molten material, whether it's magma beneath the surface or lava that has erupted onto the surface, cools down and solidifies. The word igneous itself comes from the Latin word for fire, which is quite fitting. When you hold a piece of granite or basalt, you're holding something that was once so hot it flowed like a river. The cooling process can happen quickly or slowly, and this affects what the rock looks like. Rapid cooling creates rocks with tiny crystals you can barely see, while slow cooling deep underground allows large, beautiful crystals to form over thousands of years. Sedimentary rocks have a completely different origin story. These rocks form from countless tiny particles that settle in layers over immense periods of time. Picture a river carrying sand and silt, a lake bed collecting organic material, or an ocean floor gathering the shells of countless tiny creatures. Layer upon layer accumulates, and the weight of new material pressing down on older layers gradually compacts everything together. Over millions of years, this pressure, along with minerals that act like natural cement, transforms loose sediment into solid rock. Limestone, sandstone, and shale are all examples of sedimentary rocks, and each tells us something about the environment where those sediments were deposited so long ago. The third major type, metamorphic rocks, are rocks that have undergone a transformation. The word metamorphic means changed in form, and that's exactly what happens. These rocks start as either igneous or sedimentary rocks, but then they experience intense heat and pressure that fundamentally changes their structure without actually melting them completely. It's a bit like how a caterpillar transforms into a butterfly, though the process is far slower and involves geological forces rather than biological ones. The heat might come from being buried deep in the Earth's crust, and the pressure might result from tectonic plates colliding. Marble, which starts as limestone, and slate, which begins as shale, are both beautiful examples of metamorphic rocks. Now, what exactly are rocks made of? They're composed of minerals, which are naturally occurring solid substances with specific chemical compositions and crystal structures. Quartz is one of the most common minerals you'll find in rocks, appearing in everything from granite to sandstone. It's remarkably hard and resistant to weathering, which is why quartz-rich beaches have such lovely sand. Calcite is another widespread mineral, forming the primary component of limestone and marble. When you see a cave with stalactites and stalagmites, you're looking at calcite deposits that formed drop by drop over countless years. Olivine is a beautiful green mineral often found in basalt and other igneous rocks formed from magma that comes from deep in the Earth's mantle. And mica, with its distinctive sheet-like structure that allows it to split into thin, flexible layers, adds sparkle to many rocks and catches the light in the most enchanting ways. Among all the rocks in the world, pumice stands out as truly extraordinary. This volcanic rock has an unusual property that surprises nearly everyone who learns about it. Pumice can actually float on water. This seems to defy logic at first. After all, rocks are supposed to sink, aren't they? But pumice forms during explosive volcanic eruptions when lava filled with gas bubbles cools so rapidly that those bubbles become trapped inside the rock. The result is a stone so filled with tiny air pockets that it's less dense than water. If you've ever used a pumice stone to smooth rough skin, you've held one of nature's most peculiar creations in your hand. Large pumice rafts can sometimes float across oceans after volcanic eruptions, traveling for thousands of miles before eventually becoming waterlogged and sinking. When we think about the age of rocks, the numbers become almost incomprehensible. The Acasta gneiss, found in Canada's Northwest Territories, has been dated to approximately 4.03 billion years old. To put this in perspective, this rock formed when Earth itself was only about 500 million years old. The planet was still being bombarded by asteroids, the atmosphere was nothing like what we breathe today, and life as we know it didn't exist. This ancient gneiss, a metamorphic rock with distinctive banding patterns, has survived countless geological events, continental movements, and climate changes. It provides us with a window into the earliest chapter of Earth's history, a time so remote that imagining it challenges our understanding of deep time. If you've ever been fascinated by dinosaurs, ancient plants, or creatures from Earth's distant past, you've likely encountered fossils. These preserved remains and traces of ancient life are found almost exclusively in sedimentary rocks. This makes perfect sense when you consider how these rocks form. When a plant or animal dies and becomes buried under sediment, the layers that accumulate above it protect the remains from decomposition and disturbance. Over millions of years, minerals gradually replace the original organic material, creating a stone replica of the organism. Igneous rocks form at temperatures far too high for fossils to survive, and metamorphic rocks undergo changes that typically destroy any fossils that might have originally been present. So when paleontologists search for evidence of ancient life, They're looking through layers of sedimentary rock, reading Earth's biological history page by page. Here's something that might surprise you. Some rocks can actually grow over time. This happens through a process called crystal formation. In certain environments, minerals dissolved in water can slowly precipitate out of solution and attach themselves to existing rock surfaces. Imagine a cave where water constantly drips, carrying dissolved minerals. Each drop leaves behind a tiny amount of mineral, and over thousands of years, spectacular formations grow seemingly out of nothing. This same principle applies to certain mineral veins in rocks, where crystals gradually expand as mineral-rich fluids move through cracks and pores. It's a slow form of growth, nothing like a plant sprouting from soil, but it's growth nonetheless, demonstrating that even the seemingly static geological world is dynamic and ever-changing. On the coast of Northern Ireland, there's a place that looks almost too perfect to be natural. The Giant's Causeway consists of approximately 40,000 interlocking basalt columns, most of which are hexagonal, creating a landscape that appears almost like a vast natural pavement or the ruins of some ancient, geometric architecture. Legend says it was built by giants, but the truth is equally remarkable. About 60 million years ago, intense volcanic activity caused molten basalt lava to flow across the land. As this lava cooled, it contracted, and the contraction caused it to crack in a very specific pattern. The most efficient way for the material to fracture was to create hexagonal columns, similar to how mud cracks in polygonal patterns when it dries. The result is one of nature's most stunning displays of geometric precision, proof that the laws of physics can create beauty as striking as any work of art. These columns, some reaching up to 12 meters in height, stand as a testament to the volcanic forces that shaped this region millions of years before humans walked the earth. There are rocks in this world that challenge everything we think we know about stone. When we imagine rock, we picture something rigid, unyielding, permanent in its hardness. But deep in certain quarries, there exists a remarkable exception called itacolumite, a rare type of flexible sandstone that can actually bend. Yes, you read that correctly, bendable rock. When cut into thin slabs, this extraordinary stone can flex without breaking, almost like a piece of stiff leather or wood. The secret lies in its unique structure, where the individual quartz grains are loosely interlocked, allowing just enough movement between them to permit flexibility while still maintaining the rock's integrity. It's found in only a few places around the world, including parts of Brazil and India, and geologists sometimes call it the flexible sandstone or even articulated stone. Holding a piece of rock that bends in your hands is a surreal experience, a reminder that nature still has the power to surprise us with properties we never expected. Speaking of surprising properties, imagine walking along a beach at night with an ultraviolet light, and suddenly the ordinary-looking rocks around you begin to glow with an otherworldly orange luminescence. This is exactly what happens when you shine UV light on eupalites, rocks that contain the mineral sodalite. These fascinating stones were discovered relatively recently along the shores of Lake Superior in Michigan's Upper Peninsula, and they've captured the imagination of rock collectors ever since. The name eupalite comes from Yopa, a nickname for people from Michigan's Upper Peninsula. During the day, these rocks look quite ordinary, gray and unremarkable, blending in perfectly with countless other stones scattered along the beach. But under ultraviolet light, the sodalite within them fluoresces brilliantly, transforming a nighttime beach walk into something magical. The phenomenon occurs because sodalite absorbs UV light and re-emits it at a different, visible wavelength, creating that characteristic warm orange glow that makes these rocks so sought after. Some rocks have acoustic properties that are equally surprising. In various places around the world, there are iron-rich rocks that ring like bells when struck with a hammer or another stone. These are sometimes called ringing rocks or sonorous rocks, and they produce clear, musical tones that can echo across a landscape. The exact reason why these particular rocks ring while others don't isn't entirely understood, but it appears to relate to their internal structure and composition. The rocks need to be rich in iron, have a specific crystalline structure, and be free from cracks that would dampen vibrations. There are entire fields of ringing rocks in places like Pennsylvania, where people have been known to play simple tunes by striking different rocks in sequence. It's nature's own lithophone, a musical instrument made entirely of stone, producing sounds that are both eerie and beautiful, a reminder that rocks can engage not just our sense of sight and touch, but our hearing as well. Lightning, one of nature's most dramatic displays of power, can create its own unique type of rock in an instant. When lightning strikes sand, the incredible heat, which can exceed 30,000 degrees Celsius, melts the sand immediately. This molten material fuses together and then rapidly cools, creating a glassy, tube-like structure called fulgurite. The name comes from the Latin word for lightning, and these formations are also sometimes poetically called petrified lightning. Fulgurites can extend several feet underground, following the path the lightning took as it discharged into the earth. They're typically hollow tubes with rough, sandy exteriors and smooth, glassy interiors, and they're incredibly fragile, often breaking apart when you try to excavate them. Each fulgurite is completely unique, a frozen moment of one of nature's most powerful electrical events, transformed from countless grains of sand into a singular object in a fraction of a second. Finding one is like discovering a physical trace of a lightning bolt, solid evidence of energy that's normally too fleeting to capture. When we think of famous landmarks carved from stone, Mount Rushmore immediately comes to mind. The four presidential faces gazing out over South Dakota's Black Hills are carved from granite, one of the most durable igneous rocks on Earth. The sculptor, Gutzon Borglum, specifically chose this location because the granite there is exceptionally hard and resistant to erosion, ensuring that the monument would endure for thousands of years. Granite forms deep underground as large bodies of magma cool very slowly, allowing large crystals of quartz, feldspar, and mica to develop. This coarse-grained texture gives granite its characteristic speckled appearance and contributes to its strength. The Mount Rushmore granite is particularly fine-grained for granite, which made it somewhat easier to carve while still being durable enough to withstand centuries of weathering. The monument has become such an icon that we sometimes forget we're looking at natural stone, shaped by human hands but existing as rock for millions of years before anyone imagined carving faces into it. There are rocks that form through a process so specific and unusual that when you see them, you're witnessing the result of a perfect storm of geological conditions. Septarian nodules are among these rarities. These fascinating formations begin as balls of mud on ancient sea floors. As these mud balls dry out, they crack and shrink, creating internal fractures that radiate from the center like the segments of an orange. Over time, minerals, particularly calcite, precipitate from groundwater and fill these cracks, creating beautiful crystalline veins that contrast strikingly with the darker mudstone. When you cut a septarian nodule open, the pattern revealed inside is absolutely stunning, with yellow or golden calcite crystals creating intricate geometric patterns against gray or brown stone. Some also contain aragonite and barite, adding even more colors to the mix. These nodules can range from tiny specimens you could hold in your palm to massive formations weighing hundreds of pounds. Each one is a work of natural art, created through a combination of desiccation, mineralization, and millions of years of patience. The rocks beneath Australia tell a story that reaches back to nearly the very beginning of Earth's existence. Some granite formations in the Jack Hills region of Western Australia exceed 4 billion years in age. While the Akastic gneiss in Canada is incredibly ancient, these Australian rocks push even further back into deep time. Within these rocks, geologists have found zircon crystals that date to about 4.4 billion years ago, making them the oldest known materials formed on Earth. These tiny crystals survived the violent early history of our planet, including the late heavy bombardment when asteroids pummeled Earth's surface. They provide crucial evidence about what conditions were like on the young Earth, suggesting that liquid water existed on the surface far earlier than previously thought. Standing on ground that old connects you to an almost incomprehensible span of time, to an Earth that was still forming its first continents, still settling into the planet we recognize today. When we talk about hardness in the mineral world, there's one substance that stands alone at the very top: diamond. This form of crystallized carbon is the hardest naturally occurring mineral known to science. On the Mohs scale of mineral hardness, which ranges from 1 to 10, diamond rates a perfect 10. This extreme hardness results from the way carbon atoms are arranged in diamond's crystal structure, bonded together in an incredibly strong three-dimensional network. This is why diamonds can cut through almost any other material, why they're used in industrial applications from drill bits to surgical scalpels, and why they've been treasured as gemstones throughout human history. It's remarkable that diamond and graphite, the soft material in pencil lead, are both pure carbon. The difference is entirely in how the atoms are arranged. Diamond forms under conditions of extreme pressure and temperature deep within the Earth, typically at depths of about 150 kilometers or more, where the pressure is intense enough to force carbon atoms into that ultra-strong configuration. While diamonds capture our imagination with their brilliance and hardness, there's another mineral that's far more important to understanding our planet, even if it's less famous. Olivine is the most abundant mineral in Earth's mantle, that vast layer of hot, dense rock that lies between the crust we live on and the metallic core at the planet's center. The mantle makes up about 84% of Earth's volume, and olivine dominates its composition. This silicate mineral has a distinctive olive-green color, which is how it got its name, and when found in gem-quality form, it's known as peridot. Olivine is relatively dense and forms under high temperatures, making it perfectly suited to the mantle's conditions. When volcanic eruptions bring mantle material to the surface, olivine crystals often come along for the ride, giving us actual samples of the deep Earth. Some volcanic islands, like certain beaches in Hawaii, have sand that's green because it's rich in olivine grains. This mineral is literally the foundation of our world, making up the bulk of the rock beneath our feet, even though we rarely see it directly. Perhaps the most important concept in understanding rocks is that they're not permanent in their current form. Rocks are constantly cycling between the three main types through various processes, in what geologists call the rock cycle. Imagine granite, an igneous rock, exposed at Earth's surface through the uplift of mountains. Weathering breaks it down into sediment, which washes into rivers and eventually settles in layers on an ocean floor, becoming compressed into sedimentary rock like sandstone. If tectonic forces push this sandstone deep into the Earth, heat and pressure transform it into metamorphic rock like quartzite. If it goes even deeper and gets hot enough, it melts completely, becoming magma. When that magma cools, it forms igneous rock again, completing the cycle. This cycle operates on timescales of millions of years, but it's constantly happening. The rock beneath your feet right now might have been a different type of rock millions of years ago and will likely transform into something else millions of years from now. Nothing in geology is truly permanent. Everything is in motion, changing form through the immense forces and vast timescales that characterize our dynamic planet. Among the many remarkable rocks on Earth, there's one that has fascinated humans for thousands of years because of a property that seems almost magical: lodestone, a naturally magnetic rock. Unlike most stones you might pick up, lodestone can attract iron objects and even other magnetic materials without any human intervention or processing. This extraordinary stone is rich in magnetite, an iron oxide mineral with the chemical formula FeO, and under certain natural conditions, magnetite becomes permanently magnetized, transforming into lodestone. Ancient peoples discovered these magnetic rocks long before they understood magnetism, and they used them to create the first compasses, forever changing navigation and exploration. The name lodestone comes from an Old English word meaning course or journey, reflecting its use in guiding travelers. When you hold a piece of lodestone and watch it pull iron filings toward itself, you're experiencing one of nature's invisible forces made tangible, a reminder that rocks can possess properties that go far beyond what we can see with our eyes alone. We've already mentioned rocks that ring when struck, but it's worth exploring this phenomenon a bit more deeply because it reveals something profound about the relationship between a rock's internal structure and its acoustic properties. Sonorous rocks, sometimes called lithophonic rocks, produce clear musical tones when struck, and this ability depends on a very specific combination of factors. The rock must have a uniform, fine-grained crystalline structure without cracks or flaws that would dampen vibrations. The mineral composition matters too, with iron-rich rocks being particularly prone to this ringing quality. When you strike such a rock, sound waves travel through its internal structure, and if the conditions are just right, the rock resonates at specific frequencies, much like a tuning fork or a bell. Different rocks ring at different pitches depending on their size, shape, and composition, which means a collection of sonorous rocks can essentially become a natural xylophone. In some cultures, these rocks have been used ceremonially, their haunting tones echoing across valleys and canyons, creating music that predates any human-made instrument. It's a beautiful example of how geology and acoustics intersect, how the same forces that create mountains and continents can also create the conditions for natural music. As we push further back into Earth's earliest history, the rocks become increasingly rare and precious to science. The Nov-Wadichuk Greenstone Belt, located on the eastern shore of Hudson Bay in northern Quebec, Canada, may contain rocks that are over 4.2 billion years old, making them potentially the oldest rocks ever discovered on Earth. These ancient rocks are metamorphosed volcanic and sedimentary formations that have survived unimaginable spans of time and geological transformation. Dating rocks this old is extremely challenging, and there's ongoing scientific debate about the precise age of the Nov-Wadichuk formation, but even conservative estimates place them among Earth's most ancient materials. What makes these rocks particularly valuable is that they offer clues about conditions on the very young Earth, perhaps even containing evidence related to the origins of life itself. Some researchers have found structures within these rocks that might be fossils of ancient microorganisms, though this remains controversial. Whether they're 4.2 billion years old or slightly younger, these rocks are windows into a time when Earth was barely recognizable, when the sun was dimmer, the atmosphere was toxic by modern standards, and life, if it existed at all, was just beginning its long journey toward complexity. When we look beyond Earth to other worlds in our solar system, rocks continue to tell stories, even on planets where no human has ever walked. Sedimentary rocks found on Mars by rovers and orbiters indicate that liquid water once flowed across the Martian surface. This is one of the most significant discoveries in planetary science because sedimentary rocks, as we've learned, form from layers of sediment deposited by water, wind, or ice. The specific types of sedimentary rocks found on Mars, including mudstones and rocks with structures that look like ancient river deltas, strongly suggest that Mars once had lakes, rivers, and possibly even oceans billions of years ago. The presence of certain minerals that only form in water further supports this conclusion. Today, Mars is cold and dry, with water locked in ice caps and possibly underground, but these rocks preserve evidence of a very different past. They tell us that Mars was once a warmer, wetter world, perhaps even one where life could have emerged. Every sedimentary rock discovered on Mars is a piece of the puzzle, helping us understand not just Martian history, but also the potential for life beyond Earth and the factors that make planets habitable. Here on Earth, when we look at the composition of our planet's crust, a surprising statistic emerges. About 95% of Earth's crust consists of igneous and metamorphic rocks. This might seem counterintuitive, especially since sedimentary rocks are the ones we encounter most often at the surface, covering about 75% of the land area. The resolution to this apparent contradiction is that sedimentary rocks, while widespread at the surface, form only a relatively thin veneer over the much thicker layers of igneous and metamorphic rock below. The oceanic crust is almost entirely igneous basalt, formed at mid-ocean ridges where tectonic plates spread apart and magma wells up from below. The continental crust, while more varied, has a foundation of ancient igneous and metamorphic rocks, with sedimentary layers deposited on top. This dominance of igneous and metamorphic rocks makes sense when you consider that Earth's crust formed through volcanic activity and has been continuously recycled, melted, and transformed by tectonic processes for billions of years. Sedimentary rocks are important and tell us crucial things about Earth's surface history, but in terms of sheer volume, they're just the icing on a much larger cake. Some rocks are so unusual that their very existence tells us something profound about Earth's past. Komatiites are ultramafic volcanic rocks that formed only when Earth's mantle was much hotter than it is today. These rocks last formed extensively about 2.5 billion years ago during the Archean Eon, when temperatures in Earth's mantle were perhaps 200 or 300 degrees Celsius hotter than present-day conditions. At those extreme temperatures, magma with a composition different from anything we see in modern volcanism could reach the surface and flow as lava. Komatiite lavas were incredibly fluid, more like water than the thick, viscous lava we associate with volcanic eruptions today, and they could flow for kilometers, creating vast lava plains. The name comes from the Komati River in South Africa, where these rocks were first described. What makes komatiites particularly valuable to geologists is that they provide direct evidence of Earth's thermal history. The fact that they no longer form tells us that our planet has been gradually cooling over billions of years. Finding a komatiite formation is like discovering a temperature record from Earth's youth, preserved in stone, a reminder that our planet was once a much hotter, more volcanically active world than the one we know today. Mount Everest, the highest point on Earth's surface, standing at 8,849 meters above sea level, holds within it a remarkable geological story. The summit of Everest is made of marine limestone, rock that formed from the compressed remains of countless sea creatures on an ancient ocean floor. This fact seems almost impossible when you're standing at the roof of the world, surrounded by ice and thin air, so far from any ocean that it's hard to imagine water ever reaching these heights. But the explanation lies in plate tectonics. About 50 million years ago, the Indian subcontinent, which had been drifting northward for millions of years, collided with the Eurasian plate. This collision was so massive and the forces involved so immense that the rocks between the two plates crumpled and were thrust upward, forming the Himalayan mountain range. The limestone that now sits at Everest's peak was once at the bottom of the ancient Tessis Ocean, which separated the two continents. Fossils of marine organisms can still be found in these rocks, tiny shells and coral fragments that once lived in warm tropical waters now frozen at the top of the world. This is one of the most powerful demonstrations of geological forces, proof that even the highest mountains were once beneath the waves, and that the Earth's surface is in constant, dramatic motion. Mountains can form through various processes, and some of the most visually striking examples come from ancient lava flows that cooled in very specific ways, creating columnar jointing. We've already discussed the Giant's Causeway and its hexagonal basalt columns, but this phenomenon occurs in many volcanic regions around the world. When thick lava flows cool, they contract, and if the cooling happens uniformly from the top and bottom of the flow, the contraction creates vertical fractures that organize themselves into polygonal columns, most commonly hexagons, because this shape is the most efficient way to partition space. Over millions of years, erosion can wear away surrounding material, leaving these columns standing as dramatic cliffs or formations. Devil's Tower in Wyoming is a famous example. Rising hundreds of feet above the surrounding landscape, its sides ribbed with vertical columns that make it look almost like a massive tree stump. Similar formations exist in Iceland, Scotland, and many other volcanic regions. These columnar mountains and formations are nature's architecture, demonstrating how physical laws govern not just the strength of materials but also the patterns they form when stressed, creating beauty through pure geometry. Sometimes the most exciting fossils aren't the bones or shells of ancient creatures, but the traces they left behind in their daily lives. Rock layers preserve fossilized dinosaur footprints, trackways that show exactly where these animals walked millions of years ago. These trace fossils form when an animal walks across soft sediment like mud or wet sand, leaving impressions that are then quickly covered by another layer of sediment before they can be eroded away. Over time, as the layers compress and lithify into sedimentary rock, the footprints become permanent features. What makes footprint fossils so valuable is that they capture behavior in a way that skeletal fossils cannot. They show us how dinosaurs moved, whether they traveled alone or in groups, how fast they could run, and even provide evidence of social behavior like herding. Some trackways show adult dinosaurs walking alongside juveniles, suggesting parental care. Others show predator and prey tracks crossing the same ancient mudflat at different times, documenting the eternal drama of survival. When you look at a preserved dinosaur footprint, you're seeing evidence of a single moment in time, one step taken by a creature that has been extinct for tens of millions of years, yet whose passage across soft ground was preserved perfectly enough that we can measure the stride length and estimate the animal's size and speed. When we want to understand the very formation of our solar system, we look not just at Earth's oldest rocks, but at rocks that fell from space. The oldest known igneous meteorite formed over 4.56 billion years ago, dating back to the earliest days of the solar system's formation. These meteorites are fragments of asteroids that never became part of a planet, preserving material from the primordial solar nebula, the disk of gas and dust that swirled around the young sun before planets coalesced. Some of these ancient meteorites are differentiated, meaning they come from asteroids that were large enough and hot enough to melt and separate into layers, just like planets do, with denser metals sinking to form a core and lighter silicate minerals rising to form a mantle and crust. When we study these meteorites, we're holding pieces of worlds that almost were protoplanets that began to form but were disrupted by collisions or gravitational perturbations before they could grow large enough to become true planets. They're older than Earth itself, older than any rock you'll find on our planet's surface, and they provide the baseline date for when solid materials first began to condense from the solar nebula. These ancient space rocks are time capsules from the birth of our cosmic neighborhood, evidence of the violent, chaotic processes that eventually gave rise to the orderly system of planets we see today. The story of humanity is, in many ways, written in stone. Rocks enabled early humans to create the first tools and weapons, fundamentally shaping the course of human evolution and civilization. Before metals, before ceramics, before any sophisticated technology, there was stone. Our ancestors discovered that certain rocks, when struck against each other, would fracture in predictable ways, creating sharp edges that could cut, scrape, and pierce. Flint, chert, and obsidian were particularly prized for their ability to fracture conchoidally, producing razor-sharp edges. These simple stone tools allowed early humans to process food more efficiently, butcher animals, work wood and bone, and eventually create more complex tools. The Stone Age, that vast expanse of human prehistory lasting millions of years, is named for this fundamental relationship between humans and rocks. Different cultures developed sophisticated techniques for shaping stone, from the hand axes of early hominids to the beautifully crafted projectile points of later prehistoric peoples. Even after humans learned to work with bronze and iron, stone tools remained important in many societies. The ability to understand rocks, to recognize which types were useful and where to find them, was crucial knowledge passed down through generations. In this way, rocks weren't just passive materials waiting to be used. They were teachers, shaping human cognition and culture as our ancestors learned patience, precision, and planning through the careful work of stone knapping. Beyond tools and weapons, rocks have been valued throughout human history for what they contain. Ores are rocks and minerals that are mined for the valuable metals they contain, such as gold, silver, copper, iron, and countless others. An ore isn't just any rock that contains metal. It's a rock where the metal is concentrated enough to make extraction economically worthwhile. Gold ore, for instance, might contain only a few grams of gold per ton of rock, yet that's enough to justify the enormous effort of mining and processing. The history of civilization can be tracked through our relationship with ore deposits. Copper ores gave us the Bronze Age when mixed with tin. Iron ores enabled the Iron Age and eventually the Industrial Revolution. Today, we depend on ore deposits for everything from the steel in buildings and bridges to the rare earth elements in smartphones and electric vehicles. Mining operations tunnel deep into the earth or create vast open pits to reach these valuable rocks, extracting millions of tons of material to obtain relatively small amounts of pure metal. Every piece of metal in your home, every wire, every electronic device, began as or buried in rock formations that took millions of years to form through geological processes like hydrothermal circulation, magmatic concentration, or sedimentary accumulation. The reach of rocks into modern life extends far beyond what most people realize. Rocks and minerals are used in an astounding array of everyday products, including toothpaste, soap, and batteries. The gentle abrasive in toothpaste often comes from calcium carbonate, derived from limestone or from silica. Talc, one of the softest minerals, is used in powders and cosmetics for its smooth texture. Lithium, extracted from certain minerals and brines, has become crucial for rechargeable batteries in everything from laptops to electric cars. Salt, or halite, is a rock mineral we literally consume every day. Glass is made from melted quartz sand. Ceramics come from clay minerals. Even paper often contains kaolin, a clay mineral that makes the surface smooth and bright white. The concrete and asphalt that form our roads and buildings are made from crushed rock and minerals. Gypsum, a soft sulfate mineral, becomes drywall that forms the interior walls of most modern buildings. When you look around your home or office, you're surrounded by products that either are rocks, come from rocks, or were made using rock-derived materials. Our modern technological society rests on a foundation of geology, on our ability to identify, extract, and transform the mineral wealth that Earth's geological processes have concentrated over billions of years. When we try to grasp the mineral diversity of our planet, the numbers are staggering. Earth's crust contains over 3,000 known minerals, each with its own unique chemical composition and crystal structure. This incredible variety results from the many different chemical elements available and the countless combinations of temperature, pressure, and chemical conditions under which minerals can form. Some minerals are incredibly common, like quartz and feldspar, which together make up the majority of Earth's continental crust. Others are extraordinarily rare, found in only a handful of locations worldwide, formed under such specific conditions that their very existence is remarkable. New minerals are still being discovered regularly as geologists explore remote regions, examine meteorites, or investigate unusual geological settings. Each mineral is like a word in the vocabulary that Earth uses to tell its story. By learning to read minerals, geologists can determine what conditions existed when a rock formed, what chemical reactions took place, and what the rock has experienced since. This mineral diversity isn't just scientifically interesting, it's also practically important because different minerals have different properties and uses. The 3,000 known minerals represent a vast library of materials, each with potential applications we're still discovering. Deep within the Earth, magma doesn't remain uniform as it rises toward the surface. Through a process called magma differentiation, the composition of magma changes, generally increasing in silica content as it rises and evolves. This happens because different minerals crystallize at different temperatures. As magma cools, minerals with higher melting points crystallize first and, being denser, often sink out of the liquid magma. This removes certain elements from the remaining liquid, changing its composition. The minerals that crystallize early are typically rich in iron and magnesium but poor in silica. As these minerals are removed, the remaining magma becomes progressively richer in silica and other elements like potassium and sodium. This process can transform a single body of magma into multiple rock types. A magma that starts with a basaltic composition, relatively low in silica, might evolve to produce andesite, then dacite, and eventually rhyolite, each progressively richer in silica. This differentiation is why we see such a variety of igneous rocks even though they all ultimately come from the mantle. It's also why the most explosive volcanic eruptions tend to involve silica-rich magmas, because higher silica content makes magma more viscous, trapping gases that eventually explode outward with tremendous force. Understanding magma differentiation helps geologists predict volcanic behavior and understand the chemical evolution of Earth's crust over geological time. When we survey the rocks that make up our planet's surface, one type dominates vast areas that we rarely see directly. Basalt forms most of the ocean floor and many volcanic islands, making it arguably the most volumetrically important rock type at Earth's surface. This dark, fine-grained igneous rock forms when low silica magma erupts and cools relatively quickly. At mid-ocean ridges, where tectonic plates pull apart, basaltic magma wells up continuously from the mantle, solidifying to create new oceanic crust. This process has been happening for hundreds of millions of years, spreading the ocean floor outward from the ridges. Eventually, this oceanic basalt is subducted back into the mantle at tectonic boundaries, completing the cycle. Many famous volcanic islands, from Hawaii to Iceland to the Galapagos, are built primarily from basalt. The dark lava flows, smooth ropey pahoho textures, and rough clinker-like AA flows that characterize these volcanic landscapes are all basalt. Because basalt is so common and forms from mantle-derived magma without much differentiation, studying basalt helps us understand the composition of Earth's mantle and the fundamental processes of plate tectonics. The fact that most of the ocean floor is basalt means that this rock type, though less familiar to us than continental rocks, is actually the foundation beneath much of Earth's surface, hidden beneath miles of water but fundamental to how our planet works. Among the many rocks that served ancient humans well, chert holds a special place. This rock, composed of microcrystalline quartz, was once one of the most important materials for making tools. Chert forms when silica precipitates from water or accumulates from the microscopic silica skeletons of organisms like diatoms and radiolarians. The result is an incredibly fine-grained rock that fractures in a controlled, predictable manner, creating edges that can be sharper than modern surgical steel. Chert goes by many names depending on its color and origin. Flint is a dark variety, jasper is reddish, and agate is banded. Prehistoric peoples quickly learned where to find good quality chert and would often travel considerable distances to obtain it or trade for it. Archaeological sites are littered with chert flakes, the debris from tool-making activities, and studying these flakes can tell archaeologists about ancient trade networks, technological knowledge, and cultural practices. Even after metal tools became available, chert remained useful because it could create sparks when struck against iron or steel, making it essential for starting fires. Those sparks are actually tiny pieces of iron heated to incandescence by the friction of the strike, but it's the chert's hardness that makes the process work. In some parts of the world, traditional methods of starting fires with chert and steel persisted into modern times. Some rocks cool so rapidly that they don't have time to form crystals at all, creating instead a natural glass. Obsidian forms from rapidly cooled lava, usually when lava erupts explosively into the air or flows into water, cooling within seconds or minutes rather than the hours, days, or years typical of other volcanic rocks. The result is a volcanic glass, usually black or dark brown, though it can have bands of color from impurities. Obsidian has no crystal structure. Its atoms are frozen in the random arrangement of a liquid, making it technically a supercooled liquid rather than a true solid in the crystallographic sense. This glass structure allows obsidian to fracture into edges even sharper than chert, with cutting edges only a few molecules thick. Ancient peoples prized obsidian for making the finest blades, and it was widely traded in many parts of the world. The Aztecs crafted obsidian into ceremonial knives, mirrors, and even clubs embedded with obsidian blades called macuahuitl. Some surgeons today use obsidian scalpels for certain delicate procedures because they can be sharper than steel and cause less tissue damage. Obsidian also has the interesting property of slowly absorbing water over time, and by measuring how deeply water has penetrated into an obsidian artifact, archaeologists can estimate its age through a technique called obsidian hydration dating. The interaction between rocks and light reveals hidden properties that can be absolutely spectacular. Fluorite, a mineral composed of calcium and fluorine, can fluoresce under ultraviolet light, emitting visible light in response to the UV radiation. In fact, the phenomenon of fluorescence is named after fluorite. Under normal light, fluorite can be purple, green, blue, yellow, or colorless, forming beautiful cubic crystals. But shine a UV light on certain specimens, and they glow with brilliant blues, purples, or other colors. This happens because the UV light excites electrons in the fluorite's crystal structure to higher energy states, and when those electrons fall back to their normal states, they release energy as visible light. Not all fluorite fluoresces. The property depends on trace impurities and defects in the crystal structure. Fluorite has been used for many purposes throughout history. Because of its low refractive index and low dispersion, high-quality fluorite is used in optical instruments like telescope and microscope lenses. It's also the primary source of fluorine, which goes into everything from toothpaste to refrigerants. But for many people, fluorite's appeal is purely aesthetic. Mineral collectors prize fluorescent fluorite specimens, displaying them under UV lights to reveal their hidden glow, a reminder that rocks can surprise us with properties we can't see under ordinary conditions. There's a mineral that has fooled countless amateur prospectors throughout history, a mineral so perfectly golden and metallic that it earned a nickname that's both descriptive and slightly mocking: fool's gold. Pyrite naturally forms cubic crystals and closely resembles gold in color and metallic luster. The name pyrite comes from the Greek word for fire because it creates sparks when struck against steel, similar to flint. Pyrite is iron sulfide, much harder than gold and with a different crystal structure, but to the untrained eye, especially when found in a stream bed glinting in the sunlight, it can be remarkably convincing. Many an eager prospector during gold rushes has returned home disappointed after discovering their glittering find was pyrite rather than gold. A simple test reveals the difference. Gold is soft and malleable while pyrite is brittle. Gold has a yellow streak when scraped across and glazed porcelain, while pyrite streak is greenish-black, and gold is much heavier for its size. Despite its reputation, pyrite isn't worthless. It's been used as a source of sulfur and sulfuric acid, and in the past, it was sometimes processed to extract the small amounts of gold that can be associated with pyrite deposits. Pyrite's perfect cubic crystals, often with striated faces, are geometrically beautiful and highly collectible. The mineral also forms other shapes, including a 12-sided form called a pyritohedron. In sedimentary rocks, pyrite often replaces organic material, creating stunning fossils rendered in brassy gold. So while pyrite may have disappointed prospectors dreaming of wealth, it's a fascinating mineral in its own right, demonstrating how nature can create geometric perfection and metallic beauty from simple iron and sulfur. In the depths of the Naka mine in Chihuahua, Mexico, there exists a chamber that seems to belong more to science fiction than geology. The Cave of Crystals contains selenite crystals of almost incomprehensible size, and the largest of these transparent giants weighs more than 55 tons. These colossal crystals, some reaching over 11 meters in length, formed in a cave that was once filled with mineral-rich hot water. For hundreds of thousands of years, the conditions remained nearly constant, allowing the selenite, a transparent variety of gypsum, to grow slowly and continuously into these massive beams of crystal. The cave remained at approximately 58 degrees Celsius, just below the temperature at which selenite dissolves, creating perfect conditions for growth. When miners accidentally discovered the cave in the year 2000, They found a landscape unlike anything else on Earth, with massive translucent crystals crisscrossing the space like the pillars of some ancient crystalline cathedral. The cave is so hot and humid that humans can only survive inside for minutes without special cooling equipment, as the combination of heat and 100% humidity prevents the body from cooling itself through perspiration. These giant selenite crystals represent one of nature's most extreme expressions of crystal growth, a testament to the power of stable conditions maintained over geological timescales. Throughout human history, minerals have been used in ways that might surprise us today. Graphite, the same soft carbon mineral we use in pencil lead, was once used as eyeliner in ancient civilizations. The ancient Egyptians, along with other cultures around the Mediterranean and in Asia, ground graphite into fine powder and mixed it with oils or water to create kohl, a dark cosmetic applied around the eyes. This wasn't just about beauty. The dark liner helped reduce glare from the intense sun and may have had some antibacterial properties that protected against eye infections. Graphite's ability to leave a dark mark comes from its crystal structure, where carbon atoms are arranged in sheets that slide easily over each other, allowing thin layers to transfer onto other surfaces. This same property makes graphite an excellent lubricant and, of course, useful for writing. It's remarkable to think that the same mineral that ancient peoples used to adorn their eyes is now used in everything from pencils to lithium-ion batteries to nuclear reactors. Graphite and diamond are both pure carbon, but their dramatically different properties show how the arrangement of atoms determines a material's characteristics. While diamond is the hardest natural material, graphite is one of the softest, yet both have played crucial roles in human civilization. Some minerals form crystals so geometrically perfect and colorful that they look more like abstract art than natural formations. Bismuth, a metal element, forms colorful geometric crystal structures that are among the most visually striking in the mineral world. When bismuth crystallizes, it forms what's called a Hopper crystal, where growth happens faster at the edges than in the center, creating stepped, stair-like structures. These crystals often have a distinctive rainbow iridescence, displaying blues, yellows, pinks, and greens in a metallic sheen. This rainbow effect comes from a thin oxide layer that forms on the crystal surface, and like oil on water, this layer interferes with light waves to produce the colors. Most bismuth crystals you'll see in collections are actually lab-grown rather than natural, as natural bismuth crystals are much rarer and less dramatic. Growing bismuth crystals at home is a popular activity among mineral enthusiasts because it's relatively safe and produces stunning results. Bismuth has the interesting property of being one of the few substances that expands when it solidifies from liquid, similar to water forming ice. It's also one of the heaviest stable elements, and it has various practical applications, from cosmetics to medicines to low melting point alloys. But for many people, bismuth's appeal is purely aesthetic, these rainbow-colored geometric crystals looking like something that belongs in a futuristic sculpture garden rather than on a periodic table. When space rocks slam into Earth with tremendous violence, they don't just create craters, they also create unique types of rocks. Tektites are glassy rocks formed by meteorite impacts, though interestingly, they're not pieces of the meteorite itself. Instead, tektites form when the intense heat and pressure of an impact melts terrestrial rocks and soil, flinging the molten material into the air. This material cools rapidly as it flies through the atmosphere, sometimes traveling hundreds of kilometers from the impact site, solidifying into glassy objects with distinctive shapes. Tektites often have smooth, aerodynamic forms, sometimes with grooves and patterns that record their flight through the air. They're typically black or dark brown, though some can be green or other colors. Different tektite fields around the world are associated with specific impact events. Moldavites, found in the Czech Republic, are beautiful green tektites associated with the Reese crater impact in Germany. Australites from Australia have particularly striking forms, often button-shaped with flanged edges. Tektites have fascinated humans for millennia, and various cultures have attributed mystical properties to them, not knowing their cosmic origin. Today, they're prized by collectors and worn as jewelry, each piece a tangible connection to a moment of cosmic violence when Earth and space collided with world-changing force. The properties of minerals can sometimes surprise us with their complexity. Kyanite, an aluminum silicate mineral, has different hardness depending on the direction you test along its crystal structure. This property, called anisotropism, means that kyanite can have a hardness of about 4 to 4.5 on the Mohs scale when tested parallel to the length of its blade-like crystals, but a hardness of 6 to 7 when tested perpendicular to that direction. This makes kyanite unusual among minerals and can be confusing for people trying to identify it. The name kyanite comes from the Greek word for blue, and indeed, this mineral typically forms beautiful blue blade-like crystals, though it can also be white, grey, or even green. Kyanite forms under high-pressure conditions in metamorphic rocks, and its presence helps geologists understand the conditions that existed when a rock formed. The directional hardness comes from kyanite's crystal structure, where aluminum and silicon atoms are arranged in chains. Breaking across these chains requires more energy than breaking parallel to them. This same principle explains why many minerals have cleavage planes, preferred directions along which they split. Kyanite is used as a refractory material in high-temperature industrial applications and occasionally as a gemstone, though its directional hardness makes it challenging to cut and polish. Throughout history, certain stones have carried complex and sometimes contradictory meanings across different cultures. Opal, with its distinctive play of color, carried mixed cultural symbolism, viewed as a stone of luck in some traditions and misfortune in others. Ancient Romans considered opal a symbol of hope and purity, among the most precious of gems. Aboriginal Australians, in whose land some of the world's finest opals are found, have creation stories involving opal's origin. However, in medieval Europe and later Victorian times, opal gained a reputation as unlucky, possibly reinforced by a plot element in Sir Walter Scott's novel where an opal brings misfortune to its owner. This superstition damaged the opal market for years, though it has since recovered, and opal is now appreciated worldwide for its beauty. The play of color in opal, where flashes of rainbow hues seem to move within the stone, comes from its unique structure. Opal consists of tiny silica spheres arranged in a regular pattern, and light diffracting through this structure creates the colors. Unlike most gemstones, opal contains water, typically between 3 and 10%, trapped within its structure. This makes opal somewhat delicate. It can crack if it dries out too quickly or is exposed to sudden temperature changes. Each opal is unique, with its own pattern of colors and flashes, making every piece of opal jewelry genuinely one of a kind. Ancient peoples often attributed healing properties to stones, sometimes based on sympathetic magic where a stone's appearance suggested its use. Bloodstone, a dark green variety of chalcedony spotted with red jasper, was believed to stop bleeding in ancient medicine. The red spots looked like drops of blood, and by the logic of medieval medicine, this meant the stone must be useful for blood-related ailments. Bloodstone was ground into powder and taken internally, or the stone was held against wounds. Of course, We now know that bloodstone has no actual medicinal properties for stopping bleeding, but the belief persisted for centuries and made bloodstone highly valued. Also called heliotrope, bloodstone was also thought to have other mystical properties, including making the wearer invisible according to some traditions. Despite lacking any real healing power, bloodstone remains a popular stone in jewelry and carvings, appreciated for its attractive appearance, that deep green with dramatic red spots. It forms when iron oxide minerals create the red coloration within green chalcedony, itself a microcrystalline form of quartz. The history of bloodstone reminds us how humans have always sought meaning and utility in the natural world, sometimes projecting our hopes and beliefs onto objects that, while beautiful, don't actually possess the powers we imagine. Some minerals seem designed to evoke feelings of peace and tranquility through their very appearance. Celestite, named after the Latin word for heavenly, forms pale blue crystals often found in geodes. These delicate sky blue crystals, sometimes nearly white, sometimes deeper blue, have a gentle appearance that has made celestite popular among mineral collectors and in metaphysical communities. Celestite is strontium sulfate, and it typically forms in sedimentary environments, often in association with limestone and gypsum. When you crack open a geode and find the interior lined with pale blue celestite crystals, it's a moment of genuine wonder, like discovering a pocket of sky frozen in stone. The crystals are usually translucent and have a glassy luster, and they can form in various habits, from stubby prismatic crystals to delicate blade-like formations. While celestite makes beautiful specimens, it's relatively soft and fragile, with a hardness of only 3 to 3.5 on the Mohs scale, so display pieces need to be handled carefully. Commercially, celestite is the primary ore for strontium, which has applications in fireworks, producing the brilliant red colors in pyrotechnic displays. But for most people encountering celestite, it's the aesthetic appeal that matters, those peaceful blue crystals seeming to hold within them something of the calm of a clear sky. In the world of gemstones, many are named after the people who discovered them or contributed to their study. Kunzite, a pink to lilac variety of the mineral spargimine, is a gemstone named after George Frederick Kunz, a legendary gemologist who worked for Tiffany & Company in the late 19th and early 20th centuries. Kunz was one of the most influential gemologists in American history, discovering several minerals and writing extensively about gems. Kunzite was first described in 1902 from material found in California, though it's now known from several locations worldwide. The pink color comes from traces of manganese within the crystal structure. Kunzite has an interesting property called pleiochroism, where the stone appears different colors when viewed from different angles, shifting from pink to colorless or light violet depending on the orientation. This makes cutting kunzite challenging, as lapidaries must orient the stone carefully to show the best color. Kunzite can also fade if exposed to strong light for extended periods, so some collectors store their kunzite in dark places to preserve the color. Despite these quirks, kunzite is a beautiful gemstone with a delicate, romantic appearance, and it remains popular in fine jewelry. The stone represents not just natural beauty but also the human passion for understanding and celebrating the mineral world, commemorating Kunz's contributions every time someone admires a piece of kunzite jewelry. Beauty in the mineral world sometimes comes with a price, and collectors must be aware that some stunning specimens require careful handling. Wulfenite, a lead molybdate mineral, is prized by collectors despite being toxic. This mineral forms spectacular crystals, often in brilliant orange, red, or yellow colors, with a bright resonance to adamantine luster. The crystals are frequently thin, tabular squares that look almost too perfect to be natural. Wulfenite forms in the oxidized zones of lead ore deposits, where weathering and chemical reactions create secondary minerals. Some of the finest specimens come from mines in Arizona, particularly the Red Cloud mine, which has produced exceptional crystals. The challenge with wulfenite is that it contains lead, a toxic heavy metal that can accumulate in the body with repeated exposure. Collectors should wash their hands after handling wulfenite specimens and certainly should never put them in their mouths or create dust by grinding or breaking them. Despite this caution, wulfenite is safe to collect and display if treated with appropriate respect. The same toxicity that requires careful handling doesn't diminish the mineral's beauty or scientific interest. Wulfenite crystals represent some of nature's finest work in color and form, tiny squares of orange or red brilliance that demonstrate how even potentially dangerous substances can create something visually remarkable. In the mineral world, as in life, beauty and danger sometimes coexist, and wisdom lies in appreciating both while exercising appropriate caution. The way light interacts with minerals can produce effects that seem almost magical, and certain minerals display this more dramatically than others. Certain tourmalines change color depending on their thickness, a property that makes them particularly fascinating to gemologists and collectors. Tourmaline is actually a group of closely related minerals with complex chemistry, and they come in virtually every color imaginable. Some varieties, particularly those with chrome or vanadium content, show strong dichroism, meaning they appear different colors when viewed from different angles. But the thickness-dependent color change is something else entirely. When you look at a thin slice of certain tourmalines, particularly some green varieties, the stone might appear one color, but as you look through thicker sections, the color deepens or even shifts to a different hue entirely. This happens because of how the crystal structure absorbs different wavelengths of light. As light passes through more material, more of certain wavelengths are absorbed, changing the transmitted color. Some tourmalines are intentionally cut thin to show lighter colors, while others are cut thick to enhance deep, saturated hues. There are also tourmalines that show multiple colors within a single crystal, with pink centers and green outer zones, creating stones called watermelon tourmaline. The incredible variety within the tourmaline group makes it endlessly interesting, and the way these crystals play with light reminds us that color in minerals isn't simply a matter of pigment but of complex interactions between matter and electromagnetic radiation. Some rocks are valued not for their beauty but for their content, and entire landscapes have been shaped by the search for these materials. Itabarite is a metamorphic rock rich in iron ore, found primarily in Brazil, where it forms important iron deposits. The name comes from Itabira, a region in Minas Gerais state known for its iron mining. Itabarite forms when iron-rich sedimentary rocks undergo metamorphism, transforming them into alternating bands of iron oxide minerals like hematite and magnetite along with quartz. This banding gives Itabarite a distinctive striped appearance, with dark metallic bands alternating with lighter quartz-rich layers. Brazil has some of the largest iron ore deposits in the world, and Itabarite formations are a major source of this ore. Iron extracted from these rocks becomes the steel that builds cities, vehicles, and infrastructure worldwide. The presence of Itabarite tells us something about Earth's ancient history, as many iron-rich sedimentary rocks, called banded iron formations, date back to a time when Earth's atmosphere was changing, when photosynthetic organisms were beginning to produce oxygen that reacted with dissolved iron in the oceans, causing it to precipitate and accumulate on the seafloor. These ancient deposits, later metamorphosed into rocks like atabarite, are not just economically important. They're records of one of the most profound changes in Earth's history, the oxygenation of our atmosphere. Nature sometimes creates patterns and structures that look so regular, so geometric, that they seem artificial. The tessellated pavement, found in Tasmania, Australia, is a remarkable example of this phenomenon. This formation consists of cracked siltstone that has been shaped by waves and weathering into a pattern that looks remarkably like carefully laid tiles or pavement. The rectangular blocks are separated by deep grooves, creating a surface that appears to have been constructed rather than formed naturally. The process begins with natural joints and fractures in the rock, which are then enlarged by erosion. Salt crystallization in the cracks, along with the grinding action of sand and pebbles moved by waves, deepens the grooves between blocks. Interestingly, some blocks are raised while others are depressed, creating a dome pattern. The raised areas form because they're more resistant to erosion, while the depressions occur where softer material or more intense fracturing allowed greater weathering. This differential erosion creates the dramatic relief that makes the tessellation so striking. Walking across the tessellated pavement is a surreal experience, as your mind insists this must be a human construction even while you know it's entirely natural. It's a perfect example of how geological processes, given enough time, can create order out of chaos, producing patterns that seem to follow some hidden blueprint even though they're simply the result of physics, chemistry, and time. In the heart of the Sahara Desert, visible even from space, lies one of Earth's most intriguing geological features. The Eye of the Sahara, also known as the Richat structure, is a massive circular geological structure nearly 50 kilometers across. For years, geologists debated its origin. Some thought it might be an impact crater from an ancient meteorite, while others proposed volcanic explanations. The truth, it turns out, is less dramatic but no less fascinating. The Richat structure is a deeply eroded geological dome, where layers of sedimentary rock have been pushed upward and then worn away by wind and occasional water over millions of years. The circular pattern comes from the concentric layers of different rock types, each eroding at different rates, creating the distinctive rings that make it look like a giant eye staring up from the desert. Harder layers form ridges, while softer layers erode into valleys, and the overall symmetry is remarkably precise. The structure dates back hundreds of millions of years to the Proterozoic Eon, and it provides geologists with a rare three-dimensional view of rock layers that are usually buried. For astronauts, the Eye of the Sahara serves as a landmark easily recognizable from orbit. For those who visit it on the ground, it's a reminder of how tectonic forces and erosion can collaborate to create features of stunning regularity and scale. Scattered across prairies and grasslands in certain parts of North America are mysterious formations that have puzzled scientists for generations. Mima mounds are low, rounded hillocks that dot the landscape in regular patterns, and they contain stones and soil in specific arrangements. These mounds typically range from 0.5 meter to 2 meters in height and can be several meters across, and they often occur in fields of dozens or hundreds of mounds spread across the terrain. Their origin has been debated for over a century. Various theories have been proposed. Perhaps they were created by gophers or other burrowing animals moving soil around, or maybe they formed through freeze-thaw cycles during ice ages, or possibly seismic activity caused the soil to sort itself into these patterns. Recent research suggests that in many locations, the mounds result from a combination of factors, including bioturbation by animals, erosion patterns, and soil dynamics over thousands of years. What makes Mima mounds particularly interesting is that similar formations occur in different parts of the world, from Africa to South America, and the formation mechanism might vary by location. The stones within the mounds are often concentrated at certain levels, suggesting complex processes of sorting and accumulation over time. Standing in a field of Mima mounds gives you a sense of looking at a landscape frozen in the midst of some organizing principle, a natural pattern whose full explanation still eludes us despite decades of study. In industrial applications, we need materials that can withstand extreme conditions, and the mineral world provides some remarkable solutions. Magnesite, a magnesium carbonate mineral, resists extreme heat and is used extensively in steel production and other high-temperature applications. When heated, magnesite transforms into magnesia, also called periclase, which has an extraordinarily high melting point of about 2,800 degrees Celsius. This makes it perfect for lining furnaces, kilns, and other equipment that must endure intense heat. Magnesite forms in several ways, including through the alteration of magnesium-rich rocks like serpentinite or through precipitation from magnesium-rich waters. As a mineral specimen, magnesite is usually white or gray and often occurs in massive form rather than well-formed crystals, though occasionally you can find nice crystalline specimens. Beyond industrial uses, magnesium extracted from magnesite has numerous applications, from flares and fireworks that burn with brilliant white light to supplements and antacids. The mineral also has a role in carbon sequestration research, as the process of forming magnesite naturally captures carbon dioxide, and scientists are exploring ways to accelerate this process as a potential method for removing atmospheric carbon. It's fascinating how a relatively obscure mineral, not particularly spectacular to look at, can be so crucial to modern technology and potentially to our environmental future. For thousands of years, humans have sought to capture the world around them through art, and minerals have provided many of the pigments that made this possible. Hematite, an iron oxide mineral, was used as red pigment in ancient art, from the handprints on cave walls painted by Paleolithic peoples tens of thousands of years ago to the frescoes of ancient civilizations. The name hematite comes from the Greek word for blood, referring to the mineral's characteristic red color when powdered, though solid pieces of hematite are often metallic gray or black. Hematite is incredibly abundant, forming in various geological environments, and it can be easily ground into a powder that ranges from deep red to rust-colored. This powder, called red ochre when mixed with clay, was one of humanity's first pigments. Archaeological evidence shows that humans have been using ochre for at least 300,000 years, and possibly much longer. Beyond its use as pigment, hematite is one of the most important iron ores, and massive hematite deposits are mined worldwide for steel production. Some hematite forms in distinctive shapes, including kidney ore, which looks like clusters of rounded nodules, and specular hematite, which forms glittering metallic crystals that were used as mirrors in ancient times. The red dust of hematite has colored everything from ancient cave paintings to Renaissance frescoes, and it continues to be used in pigments today, a continuous thread of utility running through human history. When we think of precious gemstones, we often think of their beauty and rarity, but it's worth remembering that both rubies and sapphires, stones that have adorned royalty and symbolized wealth for millennia, come from the same mineral. Corundum is the source of both rubies and sapphires, with the color being the only essential difference. Pure corundum is colorless, but trace amounts of different elements produce the colors we associate with these gems. Chromium creates the red of rubies, while iron and titanium together produce the blue of sapphires. Corundum can actually be many other colors too, including pink, yellow, orange, purple, and green, and all of these colored varieties except red are classified as sapphires with color designations like yellow sapphire or pink sapphire. Corundum is the second hardest natural mineral after diamond, rating a 9 on the Mohs scale, which makes it extremely durable and perfect for jewelry that will be worn daily. This hardness also makes corundum useful as an abrasive, and synthetic corundum is produced in large quantities for sandpaper, grinding wheels, and other industrial applications. Natural corundum forms in metamorphic rocks that have been subjected to high temperatures and pressures, and the finest specimens come from specific locations like Myanmar, Kashmir, and Sri Lanka, where geological conditions have been just right to produce gem-quality crystals. The value placed on rubies and sapphires throughout history reflects not just their beauty but their durability and rarity, qualities determined entirely by corundum's crystal structure and chemistry. Geodes are nature's treasure boxes, unremarkable stones on the outside that conceal glittering crystal interiors, and some of these grow to truly enormous sizes. The largest amethyst geodes weigh over 10 tons and can be tall enough for a person to stand inside. These giant geodes form in volcanic rocks when gas bubbles in cooling lava create hollow spaces. Over millions of years, silica-rich water seeps through the rock, and dissolved silica precipitates on the interior walls of the cavity, forming quartz crystals. When trace amounts of iron are present in the right oxidation state, the crystals develop the purple color characteristic of amethyst. The largest amethyst geodes come from places like Brazil and Uruguay, where ancient lava flows created ideal conditions. These massive geodes are often cut in half to display their interiors, revealing thousands of purple crystal points all growing toward the center. Walking into a room-sized geode or even looking into a large one that's been split open is an almost overwhelming experience, surrounded by countless crystals that took millions of years to grow, hidden in darkness until humans discovered and opened them. Amethyst has been prized throughout history, once considered as valuable as ruby and emerald before large deposits were discovered. The ancient Greeks believed amethyst could prevent intoxication, and the name comes from the Greek word for not drunk. Today, while amethyst is more common and affordable than in ancient times, these giant geodes remind us that nature can still create wonders that inspire awe. In the world of blue gemstones, there's a mineral that has often been confused with one of the most famous and historically important stones. Sodalite was often mistaken for lapis lazuli, and it's easy to see why. Both are deep blue, both can contain white calcite veining, and both have been used in jewelry and decorative objects. However, sodalite and lapis lazuli are quite different when you examine them closely. Lapis lazuli is actually a rock composed primarily of the mineral lazurite, along with calcite, pyrite, and other minerals, while sodalite is a single mineral species, a sodium aluminum silicate. Sodalite typically has a slightly different shade of blue, often described as more royal or violet blue compared to lapis's azure blue, and sodalite usually lacks the golden pyrite flecks that are characteristic of lapis. Sodalite was named for its sodium content, and it forms in sodium-rich igneous rocks. While it has been used since ancient times, sodalite only became widely recognized as distinct from lapis in the 19th century. Large deposits were discovered in Canada, particularly at Bancroft, Ontario, and sodalite became more available as a gemstone and ornamental stone. Today, sodalite is appreciated in its own right rather than as a lapis substitute, carved into everything from beads to bookends, valued for its rich blue color and often interesting patterns of white calcite veining. The confusion between these minerals reminds us that gemstone identification is an art as well as a science, requiring careful observation and understanding of subtle differences. In the vast spectrum of minerals, color often holds the key to identity, and the story behind each hue reveals something about the chemistry and conditions of formation. Thulite displays a rosy pink color that comes from manganese incorporated into its crystal structure. This mineral is actually a variety of the mineral zorisite, the same species that in its blue-purple form is known as tanzanite. The presence of manganese ions substituting for some of the calcium or aluminum in zorisite structure creates that distinctive pink to rose-red coloration that makes thulite so attractive. The name thulite comes from Thule, an ancient name for Norway, where the mineral was first described. Thulite forms in metamorphic rocks, particularly those that have undergone regional metamorphism, and it's found in several locations worldwide, though significant deposits occur in Norway, Australia, and parts of the United States. The color can range from pale pink to deep rose, sometimes with white or gray matrix, creating beautiful patterns. Thulite is occasionally used as a gemstone, either cut into cabochons or carved into decorative objects, though it's not particularly well known outside collector circles. Like many metamorphic minerals, thulite tells a story of transformation, of rocks that were buried deep, heated, compressed, and chemically altered, with manganese atoms finding their way into the growing crystals to create that lovely pink color. Madagascar, an island that has been isolated from continental Africa for millions of years, has developed unique geological features along with its famous unique wildlife. Zisingi Rouge, located in the northern part of the island, features sharp limestone spires shaped by erosion into a landscape that looks almost alien. The name Zisingi comes from a Malagasy word meaning where one cannot walk barefoot, and indeed, these formations are incredibly sharp and jagged. Unlike the more famous grey limestone Zisingi elsewhere in Madagascar, Zisingi Rouge gets its name from the red color of these formations, caused by iron-rich clay mixed with the limestone. The spires form through a process called karstification, where slightly acidic water dissolves limestone along cracks and joints, gradually carving the rock into increasingly dramatic formations. Rainfall and runoff continue the erosion process, sharpening the spires and deepening the channels between them. The result is a surreal landscape of red and orange stone needles, some standing several meters tall, creating a natural maze that's beautiful but treacherous to navigate. The contrast between the red rock and the green vegetation that manages to find purchase in crevices creates striking visual patterns. Zisingi formations demonstrate how water, given enough time, can transform solid rock into delicate-looking sculptures, though delicate is deceptive, as these sharp spires can easily cut through clothing or skin. Sometimes the most spectacular geological features are created not by nature alone but through the accidental intersection of natural forces and human activity. Fly geyser, located in Nevada's Black Rock Desert, formed accidentally from geothermal drilling in the 1960s. The story begins in 1916 when a well was drilled to search for water for agriculture. The well encountered geothermal water, but it was too hot for farming purposes and was capped. Decades later, in 1964, another company drilled at the site for geothermal energy, and either through poor sealing or gradual deterioration of the original cap, geothermal water began escaping to the surface. Over the following years, minerals dissolved in the hot water began precipitating around the leak, building up layer upon layer of calcium carbonate travertine. The result is a continuously growing geyser cone now several meters tall, with multiple terraces and spouts that spray water into the air. What makes Fly geyser particularly spectacular is its coloration. Thermophilic algae, organisms that thrive in hot water colonize the wet surfaces, creating brilliant reds, oranges, and greens that streak the pale travertine. The geyser continues to grow and evolve, a living sculpture that demonstrates how quickly geological features can form under the right conditions. While Fly Geyser is technically human-caused, it has become a striking example of how geothermal processes create travertine formations, similar to those at places like Yellowstone's Mammoth Hot Springs, but compressed into decades rather than millennia. In Bolivia, on the high Altiplano Plateau, more than 3,500 meters above sea level, lies one of Earth's most surreal landscapes. The Salar de Uyuni, or Uyuni Salt Flat, spans over 11,000 square kilometers, making it the largest salt flat in the world. This vast expanse of white formed from ancient lakes that evaporated over thousands of years, leaving behind a thick crust of salt and other minerals. The salt layer, in places more than 10 meters thick, overlies a brine pool rich in lithium, making Salar de Uyuni one of the world's largest lithium reserves, increasingly important as demand grows for batteries. During the dry season, the salt flat becomes a hard, flat white surface broken into polygonal patterns as the salt contracts and cracks. But during the rainy season, a thin layer of water covers the salt, transforming the entire flat into a giant mirror that reflects the sky with such perfection that the horizon disappears, creating the sensation of walking in an infinite sky. This mirror effect has made Salar de Uyuni famous, attracting photographers and travelers seeking that otherworldly experience. The flat is so large and so level that it's used to calibrate satellites in orbit. Scattered across the salt flat are rocky outcrops called islands, the remains of ancient volcanoes that once rose from the prehistoric lake. These islands now harbor unique ecosystems, including enormous cacti that grow to heights of 10 meters or more, their roots somehow finding purchase in the harsh saline environment. Among the world's oldest metamorphic rocks are some that display optical effects rivaling any gemstone. Newmite is an iridescent metamorphic rock from Greenland that's approximately 3 billion years old, making it one of the oldest gem materials on Earth. Newmite consists primarily of two amphibole minerals, anthophyllite and jedrite, which form in thin, parallel layers that create iridescence through a combination of light interference and reflection. When you look at polished newmite, you see flashes of color, typically gold, blue, green, or red, that seem to move across the dark surface as you tilt the stone. This effect, called labradorescence or schiller, is similar to what you see in labradorite but often more subtle and complex. The name Newmite comes from Nuuk, the capital of Greenland, near where the rock was first discovered in the 1982. Newmite forms under extremely high temperatures and pressures deep in Earth's crust, and its survival for 3 billion years through various geological events makes each piece remarkable. The rock is very hard and takes an excellent polish, making it popular for jewelry and ornamental objects, though it's relatively rare and can be expensive. Holding newmite means holding something nearly as old as life on Earth, a rock that formed when the planet was young. Its iridescent flashes like messages from an almost inconceivably distant past. The presence of nickel in rocks usually indicates either meteoritic origin or specific igneous processes, and nickel-bearing minerals often have distinctive colors. Gaspite is a rare green nickel carbonate mineral that's prized by collectors and occasionally used as a gemstone. The mineral was named after the Gaspe Peninsula in Quebec, Canada, where it was first described, though significant deposits have since been found in Australia. Gaspite forms as a secondary mineral in nickel-rich ore deposits, typically through weathering and alteration processes. Its bright apple green to yellowish green color is distinctive and comes from the nickel content. In fact, gasbite is one of the few naturally occurring nickel carbonate minerals, which contributes to its rarity. As a gemstone, gasbite is soft, with a hardness of only 4.5 to 5 on the Mohs scale, which means it requires careful handling and is typically set in protective settings or used in pendants and earrings rather than rings that would see more wear. The color of gasbite is intense and opaque, quite different from the translucent greens of emerald or peridot. Australian Aboriginal peoples who lived near gasbite deposits recognized the stone and sometimes used it decoratively. Today, gasbite occupies a niche market among collectors who appreciate unusual minerals and among jewelry designers looking for something different from the typical gemstones. In the hidden spaces within rocks, where mineral-laden water circulates through cracks and cavities, some of the most delicate crystals form. Creedite forms delicate, needle-like crystals in hydrothermal environments, typically in oxidized zones of or deposits where fluorine-rich fluids are present. The mineral is a calcium-aluminum fluoride sulfate hydroxide, quite a complex chemistry that requires very specific conditions to form. Creedite crystals are usually colorless to white, though occasionally they can be pale purple or orange, and they grow in radiating clusters of acicular, meaning needle-like, crystals that can look like bursts of crystalline fireworks frozen in stone. The crystals are quite fragile and can be difficult to extract and prepare as specimens without damage. Creedite was named after the town of Creede in Colorado, where it was first discovered in silver mines. Specimens from this location and from similar hydrothermal deposits in Mexico are particularly sought after by collectors. The formation of creedite indicates that fluorine was present in the hydrothermal fluids, which tells geologists something about the chemistry of the mineralizing processes. While creedite has no particular economic importance and is too soft and fragile to be used as a gemstone, its aesthetic appeal to collectors who appreciate delicate, well-crystallized minerals makes it valuable in the mineral specimen market. Among the sulfide minerals that form in or deposits, some display crystallographic features that create particularly striking visual effects. Cubanite displays shimmering metallic twinning that makes it distinctive among copper-iron sulfides. The mineral gets its name from Cuba, though it's actually found in various locations worldwide wherever copper-rich magmatic sulfide deposits occur. Cubanite has a brassy yellow color similar to chalcopyrite, another copper-iron sulfide, and the two minerals are often found together and can be difficult to distinguish without careful examination. What makes cubanite special is its crystal twinning, where multiple crystals grow together in specific orientations, creating surfaces with distinctive parallel lines or herringbone patterns that shimmer in the light. This twinning is so characteristic that it's often a key identification feature. Cubanite isn't a major ore mineral for copper compared to more abundant minerals like chalcopyrite, bornite, or chalcocite, but its presence in a deposit indicates specific formation conditions. For collectors, well-crystallized cubanite specimens, particularly those showing the characteristic twinning clearly, are desirable additions to a sulfide mineral collection. The metallic luster and golden color catch the light beautifully, and understanding that the shimmering patterns come from the precise geometric relationships of intergrown crystals adds another layer of appreciation. In volcanic regions and around hot springs, acidic conditions and metal-rich waters create unusual secondary minerals that form delicate crusts and efflorescences. Botryogen appears as fibrous mineral crusts or powdery coatings near volcanic vents and in mines where sulfide minerals are oxidizing. The name comes from Greek words meaning cluster forming, referring to the mineral's typical habit of growing as botryoidal or grape-like clusters of tiny crystals. Botryogen is a hydrated iron sulfate mineral with a distinctive orange-red to brownish-red color. It forms when iron sulfide minerals like pyrite weather and oxidize, releasing iron and sulfate that can then precipitate as various secondary minerals depending on conditions. Botryogen requires very acidic conditions to form, typically in environments where sulfuric acid is being generated through the oxidation of sulfides. The mineral is soft and water-soluble, which means specimens need to be stored carefully away from humidity. Botryogen is never abundant enough to be an ore mineral, and its solubility and lack of durability mean it has no practical uses, but it's interesting to mineralogists because its presence indicates specific geochemical conditions. In mines, the appearance of orange botryogen and similar sulfate minerals signals acidic conditions that can be problematic for both mining operations and the environment, as acid mine drainage is a significant pollution concern. Throughout history, humans have needed to sharpen their tools and weapons, and certain rocks have proven ideal for this purpose. Novaculite is a dense, fine-grained form of microcrystalline quartz that's been used for sharpening stones for centuries. The name comes from the Latin word for razor, novacula, which tells you something about the quality of edge this stone can produce. Novaculite forms from chert through low-grade metamorphism and recrystallization, creating a rock composed of incredibly fine, tightly interlocked quartz crystals. This structure gives novaculite several useful properties. It's very hard, rating 7 on the Mohs scale like all quartz, but its fine grain size means it can abrade metal to create extremely sharp edges without creating deep scratches. The best novaculite comes from the Ouachita Mountains of Arkansas, where extensive deposits have been quarried since prehistoric times. Native Americans used Arkansas novaculite for points and blades long before Europeans arrived, and the stone continues to be quarried today for whetstones and sharpening stones used by woodworkers, cooks, and anyone who needs to maintain sharp blades. Different grades of novaculite, from coarser to finer, are used for different stages of sharpening. The finest grades, sometimes called Arkansas hardstone or surgical black, can polish a blade to a mirror finish. Working with novaculite requires patience, as sharpening on natural stones is slower than using modern diamond or ceramic sharpeners, but many people prefer the control and the edge quality these natural stones provide, continuing a tradition of stone and steel that goes back thousands of years. Deep within the Earth's mantle, hundreds of kilometers below the surface, exist conditions and materials that we rarely see. Lamproite pipes are narrow volcanic conduits that can bring diamonds and mantle minerals up from these incredible depths to the surface. Lamproites are ultrapotassic igneous rocks, meaning they're unusually rich in potassium, and they form from magmas that originate in the Earth's mantle under specific conditions. Like kimberlite, their more famous cousin, lamproite pipes can carry diamonds to the surface, though lamproites are much rarer than kimberlites. The Argyle mine in Western Australia, which was for many years the world's largest diamond producer by volume and the primary source of rare pink diamonds, was a lamproite pipe. What makes these pipes particularly interesting to geologists is that they bring up xenoliths, fragments of mantle rock that provide direct samples of material from depths we could never otherwise reach. These xenoliths might contain minerals like olivine, garnet, and pyroxene in forms that only exist under the extreme pressures deep in the mantle. When magma rises rapidly through a lamproite pipe, it can carry these dense materials upward before they have time to settle out or melt. Studying lamproite pipes and their contents gives us a window into the deep earth, helping us understand not just where diamonds come from but what the interior of our planet is made of and how it behaves. The naming of rocks can sometimes be misleading, reflecting historical classifications that don't align with modern understanding. Nepheline syenite is a rock that lacks true quartz despite its name suggesting a relationship to granite. Syenite is an igneous rock similar to granite in texture, with large, visible crystals, but is deficient in quartz and instead contains feldspar-third minerals like nepheline. These feldspar-third minerals form when magma doesn't have enough silica to make quartz, instead creating minerals with similar chemistry but less silicon. Nepheline syenite typically has a light color, often white, gray, or pink, and it forms in specific tectonic settings where unusual magma compositions develop. The rock has various industrial uses because of its chemical composition. It's used in glass and ceramics manufacturing, as the nepheline acts as a flux that lowers melting temperatures. It's also used in some filler applications, in plastics, and in other industries. Some varieties of nepheline syenite are quite attractive and take a good polish, making them suitable for dimension stone and decorative applications. The most famous nepheline syenite locality is probably the Kola Peninsula in Russia, though significant deposits exist in Canada, Norway, and elsewhere. Understanding nepheline syenite requires understanding the silica saturation of magmas, a concept that's fundamental to igneous petrology but not immediately intuitive. The presence of nepheline instead of quartz tells a specific story about the chemical evolution of the magma that formed the rock. Among gemstones, few command the prices and reverence that jade does, particularly in Asian cultures where it has been treasured for thousands of years. But jade is actually two different minerals, and jadeite is one of the most valuable gemstones on Earth, particularly in its finest imperial green variety. Jadeite is a sodium aluminum silicate, a member of the pyroxene mineral group, and it forms under very high pressure conditions, typically in subduction zones where oceanic crust is being forced beneath continental crust. The finest jadeite is a vivid, translucent green, and exceptional pieces can sell for more per carat than even the finest diamonds. Myanmar is the primary source of high-quality jadeite, and the stone has deep cultural significance in Chinese culture, where it's valued not just for its beauty but for what it represents: purity, moral integrity, and immortality. Jadeite is extremely tough, meaning resistant to breaking, because of its interlocking crystal structure, which makes it ideal for carving into intricate sculptures and jewelry that can survive for millennia. The other mineral called jade is nephrite, which is actually an amphibole rather than a pyroxene, and while beautiful and historically important, nephrite generally doesn't reach the values of the finest jadeite. Determining whether a piece of jade is jadeite or nephrite requires testing, as they can look similar to the eye but have different properties and very different values in the market. Erosion doesn't proceed at the same rate for all rocks, different compositions and structures weather at dramatically different speeds. Some sandstones erode faster than any other rocks globally, particularly those with weak cement holding the sand grains together. Sandstone consists of sand-sized particles, typically quartz grains, bound together by various cements including silica, calcium carbonate, or iron oxides. When the cement is weak or soluble, the rock can crumble rapidly. Sandstone cemented with calcite, for instance, can dissolve quickly in acidic water, while those with weak clay cements might simply fall apart when wet. Some poorly cemented sandstones in arid regions erode spectacularly fast once moisture reaches them, creating dramatic erosional features like hoodoos, arches, and slot canyons in relatively short geological timeframes. The differential erosion between sandstone layers of different hardness creates much of the spectacular scenery in places like the American Southwest, where wind and water carve preferentially along layers of softer rock while harder layers remain as protective caps or resistant walls. In contrast, very well-cemented sandstones, particularly those where silica has precipitated between grains in a process called silicification, can be extremely resistant to erosion, forming cliffs and ridges that stand for millions of years. Understanding erosion rates is crucial for everything from predicting landscape evolution to assessing how long ancient ruins will last to planning construction in areas with exposed bedrock. In the world of minerals, rarity can be measured in different ways. How widespread a mineral is geographically, how large the known deposits are, or how many individual specimens exist. By almost any measure, Painite remains one of the rarest minerals ever discovered. This borate mineral was first found in Myanmar in the 1950s by British mineralogist Arthur Payne, after whom it was named. For decades, only 2 crystals were known to exist, making Painite possibly the rarest mineral on Earth. The situation has improved somewhat since additional deposits were found in Myanmar in the early 2000s, but Painite remains extraordinarily rare. The mineral forms small, brownish to reddish crystals, and its scarcity means that even small stones are valuable to collectors. Painite's rarity comes from the very specific and unusual combination of elements and conditions required for its formation. It contains boron, aluminum, calcium, zirconium, and oxygen in a specific crystal structure, and this particular combination apparently occurs only under rare geological circumstances. The discovery of additional Painite didn't flood the market. Specimens remain scarce and expensive. For mineral collectors, owning even a tiny crystal of Painite represents acquiring something truly exceptional, a mineral so rare that the total known quantity could fit in your hand. Painite reminds us that despite centuries of mineral exploration and study, Earth still holds rarities that challenge our understanding of what's possible in the mineral world. When we survey all the sedimentary rocks on Earth, one type dominates by volume, though it often goes unnoticed because it's not particularly spectacular. Shale makes up most sedimentary rock on Earth, accounting for roughly 70% of the sedimentary rock record. Shale forms from clay and silt particles that settle in calm water environments like deep ocean floors, lakes, or floodplains. Over time, these fine particles compact and lithify into rock, often retaining the ability to split along thin layers, a property called fissility. Shale is typically gray, black, or brownish, though it can be red or green depending on the minerals present. The dominance of shale in the sedimentary record tells us something important about Earth's surface processes. Fine particles are produced abundantly by weathering and are easily transported, and much of Earth's surface sediment is deposited in low-energy environments where these fine particles can settle. Shale is economically important for several reasons. It's the source rock for much of the world's petroleum and natural gas, organic-rich shales having cooked over millions of years to generate hydrocarbons. Some shales contain enough organic material to be oil shales, which can be processed to extract petroleum, though usually at higher cost than conventional oil. In recent years, hydraulic fracturing technology has allowed extraction of oil and gas directly from shale formations, dramatically changing energy markets. Shale also weathers relatively easily, breaking down to form soil, and understanding shale is crucial for understanding landscape evolution and the global sediment cycle. Sometimes geology creates scenes that seem to defy physics, formations so improbable-looking that it's hard to believe they're natural and stable. Balancing rock formations appear stable despite narrow bases, and indeed, many of these formations have stood for thousands of years in their precarious-looking positions. These rocks form through differential erosion, where softer rock beneath a harder caprock erodes away, leaving a mushroom-shaped formation or a boulder balanced on a narrow pedestal. The process is gradual, with wind, water, temperature changes, and chemical weathering slowly removing material. The formations persist because the contact point, though narrow, is still sufficient to support the weight above, and because the harder caprock protects the pedestal from erosion from above. Famous balanced rocks exist in many places, from Arches National Park to the Garden of the Gods, each one a temporary feature on geological timescales but stable enough on human timescales to have become landmarks. Eventually, these formations will fall, either through continued erosion of the pedestal or through seismic activity, but many have stood far longer than recorded human history. Some ancient peoples considered balanced rocks sacred, seeing in them evidence of supernatural forces. Today, geomorphologists study these formations to understand erosion rates and the mechanical properties of rocks, but there's still something wonderfully whimsical about a boulder the size of a house balanced on a pedestal you could wrap your arms around. The distinction between an ornamental stone and a gemstone isn't always clear-cut, but generally speaking, gemstones are minerals that are particularly beautiful, durable, and rare enough to be valuable. When we count carefully, about 100 minerals qualify as gemstones under various definitions. This might seem like a lot, but remember that there are over 3,000 known minerals, so gems represent only a tiny fraction of mineral diversity. The traditional precious gemstones are diamond, ruby, sapphire, and emerald, all of which combine exceptional beauty, durability, and relative rarity. The category of semi-precious gemstones includes dozens of other species, from amethyst and citrine to tourmaline and topaz. Some minerals qualify as gemstones only in exceptional circumstances when they occur with unusual clarity, color, or size. For example, fluorite is a relatively common mineral, but gem-quality fluorite suitable for faceting is much rarer. The number of recognized gemstones has grown over time as new varieties are discovered and as fashions change. Some minerals that were once obscure collector's items have become mainstream gemstones, like tanzanite, which wasn't discovered until 1967 but has become one of the more popular blue gemstones. The criteria for what makes a gemstone continue to evolve as new treatments are developed, as synthetic gemstones improve in quality, and as consumers' preferences shift. In the world of gemstones and precious metals, we need standardized units to measure value, and one particular unit has become universal. 1 carat equals approximately 0.2 grams, or 200 milligrams. The carat as a unit of weight for gemstones has an ancient origin, supposedly derived from the carob seed, which was believed to have a consistent weight and was used as a natural standard on merchant scales. Of course, carob seeds don't actually have perfectly uniform weight, but the concept stuck, and eventually the carat was standardized to exactly 200 milligrams in 1907. It's important not to confuse the carat used for gemstone weight with carat, spelled with a K, which measures the purity of gold alloys. A 5-carat diamond weighs exactly 1 gram, while a 1-carat stone weighs 200 milligrams. For gemstones, price typically increases exponentially rather than linearly with carat weight, meaning a 2-carat diamond of similar quality to a 1-carat stone isn't twice the price but rather significantly more, because larger high-quality stones are disproportionately rare. Gemstones are also often described in terms of points, where 100 points equals 1 carat, so a 50-point diamond is half a carat. This system allows for precise description of stone sizes and helps establish market values. When you see a gemstone described by carat weight, You're participating in a system of measurement that has roots in ancient trade but has been refined and standardized for modern commerce. The incredible diversity of minerals in Earth's crust might seem overwhelming, but scientists have organized this complexity into a logical system. Minerals are grouped into 9 major classes based on their chemical composition and specifically based on the anion, the negatively charged component that dominates the mineral's chemistry. These classes are silicates, which contain silicon and oxygen and make up about 90% of the Earth's crust, oxides and hydroxides, where oxygen or hydroxide groups combine with metals, sulfides, where sulfur combines with metals, sulfates, containing the sulfate group, carbonates, containing the carbonate group, phosphates, containing the phosphate group, halides, where elements like chlorine or fluorine combine with metals, native elements, which occur as pure elements rather than compounds, and finally organic minerals, which form through biological processes. The silicate class is by far the largest and most important for understanding crustal rocks, as minerals like quartz, feldspar, olivine, and pyroxene are all silicates. Understanding this classification system helps make sense of mineral properties and relationships. Minerals in the same class often have related properties and form under similar conditions. For instance, carbonate minerals like calcite and dolomite both react with acid and typically form in sedimentary environments or through hydrothermal processes. This organizational framework is one of the great achievements of mineralogy, bringing order to the tremendous variety of Earth's mineral kingdom and allowing us to predict properties, understand formation processes, and recognize relationships between different minerals. It's a reminder that beneath the diversity of nature lies pattern and order, waiting to be discovered. When we look at the fundamental building blocks of our planet, one class of minerals dominates above all others. Silicates dominate Earth's crust and mantle, making up approximately 90% of the crust and essentially all of the mantle. This overwhelming dominance makes sense when you consider that silicon and oxygen, the two elements that combine to form silicates, are the two most abundant elements in Earth's crust. The basic building block of all silicate minerals is the silicon-oxygen tetrahedron, where one silicon atom sits in the center surrounded by 4 oxygen atoms arranged in a pyramid shape. These tetrahedra can exist as isolated units, can share oxygen atoms to form chains, sheets, or 3-dimensional frameworks, and this variation in structure creates the enormous diversity we see in silicate minerals. Olivine has isolated tetrahedra, pyroxenes have single chains, amphiboles have double chains, micas have sheets, and quartz and feldspars have 3-dimensional frameworks. The properties of silicate minerals, from their hardness to their cleavage to their melting points, relate directly to how these silicon-oxygen tetrahedra are arranged and connected. Understanding silicates means understanding the rocks that make up most of our planet, from the basalt of the ocean floor to the granite of continents to the peridotite of the mantle. The silicon-oxygen bond is strong and stable under a wide range of conditions, which is why silicate minerals persist through so many geological processes and why they're the foundation of the solid Earth. Not all mineral classes are as volumetrically important as silicates, but each has distinctive properties and geological significance. Halides are minerals that contain halogen elements like chlorine or fluorine combined with metals. The most familiar halide is halite, common table salt, which is sodium chloride. Halides typically form in evaporite environments where salty water evaporates, leaving dissolved minerals behind. Salt lakes, ancient seabeds, and coastal lagoons in arid climates are common settings for halide formation. Fluorite, which we've mentioned before, is calcium fluoride and forms in hydrothermal veins rather than through evaporation. Halide minerals tend to have relatively simple crystal structures and often high symmetry, forming beautiful cubic or octahedral crystals. They are generally soft, easily dissolved in water, and have relatively low melting points compared to silicates. Halite's perfect cubic cleavage, breaking along 3 perpendicular planes to form little cubes, is a classic demonstration of how crystal structure determines physical properties. Historically, halides have been extremely important to human civilization. Salt was essential for food preservation before refrigeration, valuable enough to be used as currency, giving us the word salary. Today, halite is used not just for food but for de-icing roads, in chemical manufacturing, and in water softening. Fluorite is used in metallurgy, optics, and as the primary source of fluorine for industrial processes. While halides make up only a tiny fraction of Earth's crust, their economic and historical importance far exceeds their abundance. Most minerals we encounter are compounds, combinations of multiple elements bonded together, but there's a special class of minerals that need no such partnerships. Native elements occur naturally in pure, uncombined form, and they include some of humanity's most treasured materials, such as gold and copper. Gold's occurrence as a native element is one reason it was among the first metals used by humans. It doesn't require smelting or chemical processing to extract from ore, just physical separation. Gold nuggets found in streams are pure metallic gold, ready to be shaped. Copper also occurs natively, though most copper is extracted from sulfide or oxide ores. Other native elements include silver, platinum, iron from meteorites, and the native forms of carbon, diamond and graphite. Some native elements are so reactive that they're only stable in unusual environments. Native iron on Earth's surface almost always comes from meteorites, as iron in terrestrial environments quickly oxidizes. However, deep in Earth's core, iron exists in its native metallic form under conditions of extreme pressure where oxidation doesn't occur. The native elements class also includes some nonmetals like sulfur, which can form in volcanic areas where it precipitates from sulfur-rich gases. Native elements remind us that sometimes the most valuable materials are those that nature provides in their simplest, purest form, requiring minimal processing to be useful. The fact that gold occurs natively, combined with its beauty, rarity, and resistance to tarnish, explains much of its enduring value throughout human history. We've discussed how different types of rocks form and where they occur, and there's an interesting paradox in the distribution of sedimentary rocks. Despite covering about 75% of Earth's land surface, sedimentary rocks make up a relatively small fraction of Earth's total crust by volume. Estimates suggest sedimentary rocks account for only about 5 to 8% of the crust's volume. This apparent contradiction resolves when you realize that sedimentary rocks form a relatively thin veneer over the much thicker layers of igneous and metamorphic rocks below. Sediments accumulate at Earth's surface, in oceans, lakes, river valleys, and deserts, but they don't penetrate deeply into the crust. The oldest oceanic sediments are only about 200 million years old because older ocean crust has been subducted back into the mantle. Continental sediments can be older, with some sedimentary rocks dating back over 3 billion years, but even ancient sedimentary basins are relatively shallow compared to the full thickness of continental crust, which can extend 40 kilometers or more below the surface. Below the sedimentary layers, you encounter the igneous and metamorphic basement rocks. This distribution has important implications for understanding Earth's history. While sedimentary rocks are crucial for understanding surface processes, climate history, and the evolution of life, the deeper story of Earth's formation and the processes that built continents is written primarily in igneous and metamorphic rocks. When rocks undergo metamorphism, the heat and pressure they experience can reorganize minerals in distinctive patterns. Foliated metamorphic rocks show mineral alignment, where platy or elongated minerals arrange themselves perpendicular to the direction of maximum pressure. This creates visible layering or banding in the rock. Slate, for instance, forms when shale is subjected to low-grade metamorphism, and the clay minerals recrystallize into mica minerals that align, giving slate its characteristic ability to split into thin, flat sheets. Schist forms at higher metamorphic grades and has larger, visible mica crystals all aligned in the same direction, giving the rock a shiny, flaky appearance. Gneiss forms at even higher grades and shows compositional banding, with layers of light-colored minerals like quartz and feldspar alternating with dark layers of minerals like biotite and amphibole. This foliation tells geologists about the stress conditions during metamorphism. The alignment of minerals perpendicular to pressure means geologists can determine the orientation of ancient compressive forces by examining the foliation in metamorphic rocks. In mountain belts, foliation often parallels the trend of the mountains, recording the compression that built them. Foliation also affects the physical properties of rocks, creating planes of weakness along which the rock more easily breaks, which is both useful, as in slate for roofing tiles, and problematic, as when building foundations on foliated metamorphic rocks where stability might be directionally dependent. Not all metamorphism produces the distinctive layering we see in foliated rocks. Non-foliated metamorphic rocks form without layering, typically when the parent rock is composed of minerals that don't preferentially align under pressure or when metamorphism occurs without strong directional stress. Marble, which forms from limestone or dolostone, is the classic example. The calcite or dolomite crystals in the original sedimentary rock simply recrystallize to larger crystals during metamorphism. But because calcite doesn't have a platy or elongated habit, the resulting marble shows no foliation, just a granular texture of interlocking crystals. Quartzite forms similarly from quartz-rich sandstone, with the quartz grains recrystallizing and fusing together so thoroughly that fractures typically cut across grains rather than around them, making quartzite extremely hard and durable. Hornfels is another non-foliated metamorphic rock, forming through contact metamorphism when rock is heated by proximity to magma but not subjected to the directed stress that would cause foliation. The lack of foliation in these rocks often makes them more isotropic, meaning their properties are the same in all directions, which can make them desirable for construction and sculpture. The pure white marble that Michelangelo preferred for sculpture, like Carrara marble from Italy, is metamorphosed limestone with a fine, even texture and no directional properties, allowing the sculptor to carve in any direction without the stone splitting along foliation planes. The texture of igneous rocks tells us about their cooling history, and nowhere is this more evident than in the distinction between intrusive and extrusive rocks. Intrusive igneous rocks cool slowly deep underground and form large crystals that are visible to the naked eye. When magma is injected into the crust, whether as massive plutons that will eventually become exposed as batholiths or as smaller intrusions like dikes and sills, it's surrounded by rock that insulates it, allowing cooling to proceed slowly over thousands to millions of years. This slow cooling gives crystals time to grow large. Granite is the archetypal intrusive rock, with crystals of quartz, feldspar, and mica typically several millimeters to centimeters across. In some pegmatites, which are extremely coarse-grained intrusive rocks that cool from water-rich magmas, crystals can reach sizes measured in meters. The large crystal size in intrusive rocks allows geologists to identify minerals easily and study the rock's composition in detail. These rocks also tend to be strong and durable because the interlocking crystals create a tight structure with few weaknesses. Intrusive igneous rocks make excellent building stones, which is why granite has been used for millennia in construction, from ancient Egyptian obelisks to modern countertops. The slow cooling that created these rocks billions or millions of years ago is recorded in every visible crystal, each one a tiny record of the patience of geological processes. While some magma cools slowly underground, other magma reaches Earth's surface and encounters a radically different environment. Extrusive igneous rocks cool rapidly when exposed to air or water and develop fine-grained textures where individual crystals are too small to see without magnification. Basalt, the most common extrusive rock, typically has a fine-grained texture, though it may contain some larger crystals called phenocrysts that began growing while the magma was still underground. These phenocrysts were then carried upward in finer-grained ground mass that crystallized quickly upon eruption. The rapid cooling of extrusive rocks sometimes prevents any crystals from forming at all, resulting in volcanic glass like obsidian. Pumice and scoria, which form from frothy lava filled with gas bubbles, have textures dominated by vesicles, the holes left by escaping gas, rather than by crystal size. The texture of extrusive rocks provides information about eruption conditions. A fine-grained texture indicates rapid cooling, while the presence and size of vesicles tells us about gas content in the magma. The distribution of different lava flow types around volcanoes helps volcanologists understand eruption history and predict future behavior. Extrusive rocks are the most direct evidence we have of volcanic processes, frozen moments of eruptions that occurred at timescales from seconds to days, far faster than the leisurely crystallization of intrusive rocks, but preserving equally valuable information about Earth's internal processes. As we bring our journey through the world of rocks to a close, it's worth reflecting on their overall distribution and importance. Igneous rocks cover much of Earth's land and oceanic crust, forming the foundation upon which other geological processes operate. The entire ocean floor, covering more than 70% of Earth's surface, is basaltic igneous rock, created continuously at mid-ocean ridges and slowly spreading outward. On the continents, although sedimentary rocks are visible at the surface across wide areas, the basement beneath is predominantly igneous and metamorphic, with granite and related rocks forming much of the continental foundation. Shield areas like the Canadian Shield or the African Shield expose ancient igneous and metamorphic rocks at the surface, providing glimpses of the deep crustal rocks that underlie the continents everywhere. Even many mountain ranges, once you look past the sedimentary rocks that cap peaks like Mount Everest, have cores of igneous and metamorphic rocks. The dominance of igneous rocks reflects the fundamental truth that Earth is a heat engine, with internal heat driving the melting, movement, and solidification of rock in a continuous cycle. Every igneous rock represents magma that rose from depth, carrying heat and material from Earth's interior toward the surface. Understanding igneous rocks means understanding how planets evolve, how continents form, why volcanoes erupt, and how Earth's internal heat engine has operated for over 4.5 billion years. As you rest and reflect on these facts about rocks, consider that beneath you, whether you're on land or sea, lies a foundation of stone, most of it igneous, that has been forming and reforming through countless cycles since our planet first began to cool and solidify from the swirling disk of material that would become our solar system. Rocks are not just objects to study. They are the very substance of the world we inhabit, the patient record keepers of Earth's long and continuing story, and the foundation upon which all terrestrial life, including our own, has built its existence. Sleep well, knowing that the ground beneath you is solid, ancient, and full of stories written in stone.